Across the void beyond Neptune, something moves. It crosses the ecliptic at an angle no bound object should possess. Its light curve shifts in hours, not days, too fast, too irregular. The tail point's 15 degrees off solar direction. 3 independent observatories report positional offsets that shouldn't exist under pure gravity. The spectrum shows water ice signatures at temperatures where water ice should not sublimate, and the acceleration, measured twice, confirmed, archived, exceeds what radiation pressure alone can explain. 93 incoming velocity, 31 kilometers per second relative to the Sun's rest frame. This object formed somewhere else. It spent millions of years in interstellar darkness, untouched by starlight, and now it has entered a living solar system. Either the solar system is reacting to something it has never encountered before, or our models of interstellar matter are incomplete in a way that fundamentally matters. The Discovery image appears unremarkable at first. A faint streak against background stars logged automatically by the Atlas survey system on March 18th, detection confidence moderate, flagged for review. The designation follows standard protocol, year, Hervé identifier, sequential number, 3i Atlas. The I denotes what makes it extraordinary. Interstellar origin confirmed through astrometric data spanning 6 observation windows across 72 hours. The orbital elements tell the story with mathematical precision. 932, placing it firmly in hyperbolic space in an unbound trajectory that originated beyond the Sun's gravitational sphere of influence. 3 degrees to the ecliptic plane, cutting sharply across the orbital architecture shaped by the solar system's formation disk 4.5 billion years ago. 04 astronomical units, a close approach that brings it just beyond Earth's orbit at maximum solar heating. Hyperbolic excess velocity at infinity, approximately 31 kilometers per second, the speed it possessed in interstellar space before the Sun's gravity began to curve its path. 8 astronomical units from the Sun, inbound, already bright enough to register on wide-field CCD arrays scanning for near-Earth asteroids. Follow-up observations locked the position to sub-arc-second precision. The object was real, the trajectory was unambiguous, and the timing, arriving now, detectable for perhaps 18 months before it passes perihelion and recedes forever, represented an observational window that would close whether we understood it or not. This makes it the 3rd confirmed interstellar object detected passing through the inner solar system. The first, One-Eye Oumuamua, arrived in 2017, a tumbling, elongated body that exhibited unexplained non-gravitational acceleration. The second, Two-Eye Borisov, appeared in 2020, behaving like a classical comet with a well-defined coma and predictable outgassing. Each visitor carried information encoded in its physical properties, chemical composition, structural characteristics, thermal history, information about environments we cannot otherwise sample. 3i Atlas represents the continuation of that archive, but it does not fit neatly into the taxonomy established by its predecessors. The Discovery teams followed confirmation protocols with methodical care. Astrometric positions were cross-referenced against star catalogues to eliminate parallax effects. Orbital solutions were computed using multiple dynamical models, each converging on hyperbolic geometry with statistical confidence exceeding 6 sigma. The object's motion across the sky matched predictions within measurement error. There was no ambiguity in the conclusion. This material had travelled through the interstellar medium for timescales measured in millions of years, crossing perhaps 20 parsecs of galactic space until random gravitational deflections brought it into the Sun's gravitational catchment area. What remained uncertain was everything else. Within 48 hours of public announcement, observation requests flooded scheduling systems at observatories across 3 continents and low Earth orbit. Hubble Space Telescope allocated directors discretionary time for high-resolution imaging. The James Webb Space Telescope adjusted its L2 pointing schedule to capture infrared spectroscopy during optimal solar elongation. Subaru's 8.4-meter mirror focused on photometric monitoring. ALMA coordinated millimeter wavelength observations targeting molecular emission lines. Gaia's continuous scanning provided astrometry with micro-arc-second precision. VLT equipped adaptive optics systems for surface morphology studies. Amateur networks contributed as well. Coordinated CCD photometry from backyard observatories in New Zealand, Chile, South Africa, and Arizona provided light curve coverage across longitudinal gaps in professional schedules. These independent measurements, calibrated against standard star catalogues and cross-verified through shared data repositories filled temporal windows that would otherwise remain dark. The collaborative structure mirrored the distributed nature of modern astronomy, no single instrument sufficient, no single dataset complete, but the aggregate forming a coherent whole. What emerged from this observational convergence was not simplicity, but structured complexity. Optical imaging showed a diffuse coma extending approximately 12,000 kilometers from a central condensation consistent with active sublimation of volatile material. 1 astronomical units, expected values for a dark, rapidly rotating body at that heliocentric distance. Spectroscopy revealed absorption features matching water ice, carbon monoxide, and possibly methanol or ammonia ices, though signal-to-noise ratios left compositional ratios uncertain. 3 arcseconds per observation epoch. Multiple observatories independently confirmed the object's location within error bars smaller than the angular diameter of Jupiter at opposition. This redundancy eliminated instrumental artifacts as explanations for positional anomalies. If the object appeared offset from predicted gravitational trajectories, the discrepancy was not a function of measurement error. Radio observations targeting the 18cm hydroxyl line, a signature of water photodissociation, returned tentative detections, though baseline subtraction introduced ambiguities in interpretation. Millimeter wavelength data searched for carbon monoxide emission, a common cometary tracer, but detected only upper limits, suggesting either low CO abundance or emission rates below instrument sensitivity thresholds. The consistency across platforms validated the object's physical reality while simultaneously documenting behaviors that resisted straightforward interpretation. Every instrument confirmed the object existed. None provided a complete explanation for what it was doing. Standard cometary physics establishes clear expectations. When a volatile-rich body approaches the Sun, solar radiation deposits energy into surface layers faster than thermal conduction can distribute it inward. Subsurface ices reach sublimation temperatures, transitioning directly from solid to gas without passing through liquid phase. The expanding gas drags dust particles into space, forming a coma and tail structure aligned with solar radiation pressure and the solar wind's magnetic field. This process generates a measurable thrust, non-gravitational acceleration, that depends on the object's mass, surface area, rotation state, and the distribution of active regions across its surface. 1 astronomical units should produce water ice sublimation rates on the order of 10 to 20 kilograms per second, assuming moderate albedo and typical nucleus radius between 500 meters and 2 kilometers. Dust to gas mass ratios, constrained through scattered light photometry and thermal infrared flux, suggested values near unity. 1 kilogram of dust per kilogram of gas, consistent with primitive solar system comets. Radiation pressure on ejected dust grains generates tails that curve away from the Sun, shaped by grain size distribution and ejection velocities. Larger grains, less affected by radiation pressure, trace trajectories closer to the object's orbital path. Smaller grains dominated by photon momentum transfer form extended fans pointing anti-solar. The solar wind, a continuous stream of charged particles flowing outward at 400 km per second, creates a secondary tail structure aligned with magnetic field lines, primarily visible in ion emission rather than dust scattering. These processes are well characterized. Decades of cometary observation, coupled with in situ measurements from missions like Rosetta and Deep Impact, have established robust physical models. Applied to 3I Atlas, these models predict brightness, evolution, tail morphology, and acceleration magnitudes with quantifiable uncertainty bounds. Solar radiation pressure alone, acting on cross-sectional area estimates derived from absolute magnitude, should produce accelerations on the order of 10^7 meters per second squared at 2 astronomical units, directed radially outward from the Sun. Outgassing thrust, assuming symmetric emission from a rotating nucleus, should contribute similar or slightly larger accelerations, also primarily radial but modulated by rotational phase and active region distribution. Observations, however, documented accelerations exceeding 3.10^7 meters per second squared, with directional components that could not be reconciled with purely radial forces. The discrepancy persisted across multiple orbital solution algorithms and force model assumptions. Photometric monitoring revealed a light curve that defied stable periodicity, 4 magnitudes, 25 magnitudes, 6 magnitudes over intervals as short as 90 minutes. Classical cometary nuclei exhibit stable rotation periods on timescales of weeks to months. Changes occur, but gradually, driven by torque from asymmetric outgassing, a well-understood mechanism that produces predictable spin-state evolution. I-Atlas displayed variations too rapid and too large to reconcile with standard torque models, unless the object's moment of inertia was unusually low or its active regions experienced dramatic, unpredictable shifts. Tail morphology added further complications. High-resolution imaging captured a primary dust tail extending 200,000 kilometers antisolar, as expected. But a secondary feature, narrower and oriented 15 degrees off the solar direction, persisted across multiple observation epochs. Dust dynamical models struggled to reproduce this geometry. Radiation pressure and solar wind forces, applied to reasonable grain size distributions, consistently predicted tail structures within degrees of anti-solar alignment. The observed offset required either anomalous grain properties, perhaps highly porous aggregates with unusual optical cross-sections, or an additional force component not included in standard models. Spectroscopic observations documented another inconsistency. 0 microns, varied in strength over timescales inconsistent with rotational modulation, 5 rotation periods based on the tentative 8-hour cycle, showed ice feature depths differing by a factor of 2. Either the surface ice distribution was extraordinarily heterogeneous, or sublimation rates were changing faster than thermal models predicted. Astrometric residuals, the difference between observed positions and those predicted by gravitational models, accumulated systematically. 8 arcseconds, equivalent to roughly 200 kilometers at the object's distance. 3 arcseconds, an improvement, but still 3 times larger than measurement uncertainty. The orbit wanted to deviate in a direction not fully explained by radial solar pressure or symmetric gas emission. None of these observations individually constituted crisis. Each could be accommodated with adjustments, complex rotation states, heterogeneous surface composition, asymmetric active regions, but the aggregate resisted coherent synthesis. Models that explained the light curve failed to match the tail geometry. Parameters that fit the astrometric residuals produced unrealistic mass loss rates. Every adjustment in one domain created tension in another. Conservative interpretations begin with established physics and extend minimally. Perhaps 3I Atlas possesses an unusually high fraction of super-volatile ices, carbon monoxide, methane, nitrogen, that sublimate at greater heliocentric distances and produce stronger outgassing than water-dominated models predict. Observations of 2I Borisov documented significant CO emission, demonstrating that interstellar comets can carry volatile inventories distinct from solar system analogues. Alternatively, the nucleus may consist of multiple loosely bound fragments, a gravitationally aggregated rubble pile with low bulk density and high porosity. Such structures, common among Jupiter family comets, allow gases to vent through internal pathways, creating thrust vectors that depend on interior geometry rather than surface distribution. Outgassing from subsurface voids could produce accelerations decoupled from observed surface activity patterns. Fractal dust aggregates offer another pathway. If ejected particles consist of loosely bound submicron grains forming structures with very low bulk density, their optical cross-sections could exceed geometric expectations, amplifying radiation pressure effects and altering tail morphology. Laboratory studies of interplanetary dust particles collected in Earth's stratosphere have revealed such fractal morphologies, suggesting they exist in natural cometary ejecta. More speculative models invoke phase-changing materials. Amorphous water ice, metastable at low temperatures, transitions to crystalline structure when warmed, releasing stored latent heat and trapped gases in sudden outbursts. If 3I Atlas retained amorphous ice from its interstellar cold soak, solar heating could trigger sporadic crystallization events, producing brightness and activity fluctuations uncorrelated with rotation. Swarm-like configurations, multiple small bodies traveling in close proximity, exchanging material or fragmenting under tidal stress, could generate composite light curves and complex tail structures. Observations of disrupting comets like 73P Schwassmann-Wachmann have documented such behavior. Whether fragmentation occurred before detection or during solar system passage remains uncertain, but the possibility cannot be excluded. At the boundary of conventional frameworks lies the question of deliberate structure. Non-gravitational accelerations that persist across observation epochs resistant to standard force models, superficially resemble propulsion, not rockets or engines in any engineered sense, but perhaps natural configurations, rotating bodies with highly asymmetric outgassing, directional sublimation from isolated vents, or even radiation pressure on artificially large cross-sectional areas that mimic controlled thrust. The distinction between a highly unusual natural object and a minimally functional artifact becomes difficult to define when both produce identical observational signatures. No model achieves full explanatory closure. Each framework accommodates a subset of observations while leaving others unresolved. The residuals persist. 04 astronomical units on October 12th, bringing 3I Atlas to its closest solar approach. At this distance, surface temperatures on a dark, slowly rotating body will reach 350 Kelvin, hot enough to drive vigorous water-ice sublimation and potentially trigger activity from more refractory materials. Brightness is expected to increase by 2 to 3 magnitudes, making the object accessible to smaller telescopes and enabling detailed spectroscopic studies. Post-perihelion trajectory carries the object outward through the orbital plane near Jupiter's distance in early 2027. 8 astronomical units, Jupiter's gravitational influence will subtly modify the outbound trajectory, providing a natural dynamical experiment. Astrometric measurements during this phase will test whether non-gravitational accelerations continue as solar heating declines, or whether the anomalous forces diminish with activity levels. Coordinated observation campaigns have been organized through the International Astronomical Union's Small Bodies Working Group. Priority targets include high-cadence photometry during perihelion passage, infrared spectroscopy to track volatile species evolution, and radio observations searching for hydroxyl and carbon monoxide emission at peak activity. Space-based assets will provide continuous coverage free from atmospheric absorption and diurnal gaps. Computational models are being refined in parallel. Thermophysical simulations incorporating updated volatile inventories, improved rotation state estimates, and heterogeneous surface properties will generate testable predictions for light curve evolution and outgassing rates. Dust dynamical codes will explore whether exotic grain populations, porous aggregates, metallic inclusions, organic tholins can reproduce observed tail geometries. Orbital integrators will incorporate increasingly sophisticated force models, attempting to reduce astrometric residuals to within measurement noise. The observational window extends through mid-27, after which the object will fade below detection thresholds of all but the largest telescopes. By late 2028, it will have receded beyond 10 astronomical units, returning to the cold interstellar conditions it knew before entering the Sun's domain. Whatever processes drive its current behavior will cease, freezing its state into torus or dormancy until, perhaps millions of years hence, it encounters another star. This timeline imposes constraints. Questions unresolved by mid-27 will remain unresolved indefinitely. No spacecraft intercept is feasible given current detection to launch timelines. The object will be studied remotely or not at all. Astronomy proceeds through accumulated uncertainty. Instruments capture photons, position, wavelength, arrival time, and those measurements constrain models without uniquely determining them. Ambiguities persist not through observational failure, but because nature presents complexity that exceeds our capacity for complete characterization. We build frameworks that approximate, predict, and guide expectation, but the frameworks remain human constructs, subject to revision when new data demand it. 3I Atlas carries information encoded in chemical abundances, structural properties and dynamical history, information about the environment where it formed, the processes that shaped it, and the regions of the galaxy it traversed. Every spectral line, every photometric data point, every astrometric residual adds detail to that record. But the record is partial. We observe consequences without accessing causes. We measure effects without witnessing formation. And we interpret patterns through frameworks built on solar system experience, uncertain how far those frameworks extend into the broader galaxy. The discipline of not knowing is central to the scientific method. Hypotheses are tested, not proven. Models are falsified or survive, but never confirmed with absolute certainty. The presence of unexplained observations does not constitute crisis. It constitutes the normal state of inquiry at the boundary of understanding. What matters is whether the questions posed are answerable in principle. Whether additional observations, refined models, or expanded theoretical frameworks can narrow the space of plausible explanations. For 3i Atlas, that narrowing continues. Each observation epoch reduces uncertainty in orbital parameters, constrains physical properties, and tests model predictions. The object is not becoming less mysterious through this process, but the mystery is becoming better defined, more precisely articulated, more amenable to structured investigation. The difference between knowing and not knowing is not binary. It is a gradient traversed through patient accumulation of detail. Interstellar objects represent an archive of galactic material science, sampled through rare gravitational encounters. Each visitor carries unique information, irreproducible and irretrievable once it departs. The archive is sparse, perhaps one detectable interstellar object per year, given current survey capabilities, but it is also cumulative. Patterns may emerge across multiple objects that remain invisible in individual cases. Anomalies observed here may find counterparts elsewhere, or they may stand alone, singular and unexplained. We watch because we can, we measure because the opportunity exists, and we refrain from premature conclusion because the cost of misinterpretation exceeds the discomfort of suspended judgment. The solar system continues to react. Gravity curves the trajectory, radiation heats the surface, solar wind strips ions into space, and 3i Atlas continues to respond in ways we are still learning to interpret. The interaction is mutual, the outcome uncertain, and the observations continue.